Okay, so in this video we will start doing some calculations on accelerations. We will take examples related to rigid bodies where the goal is going to be to go beyond velocities and determine acceleration variables. So that is the natural next step towards understanding different techniques in solving problems in dynamics, and so in keeping with the trend and in keeping with the main focus of these videos, we will show multiple methods of finding accelerations depending on the problem, and we will discuss about the benefits and special features of each of those methods. The problem that we will start working on is the problem of gyroscope. This is a problem that we had looked at in our earlier videos. In those videos we had looked at this problem from the perspective of velocity calculations, and so now we will go to the problems of acceleration calculations. So let us define the problem statement, and we will use some of the results that we have derived in this problem in our previous videos. So I would urge the viewers to go a few videos back, where you will see from the title of the videos where we have worked on the gyroscope problem. We have shown two methods for finding the velocity of a point on the disk of the gyroscope. So now we will go to accelerations. So we will, in the gyroscope problem, we have used the spherical coordinates, and so we will continue to do that. So let me just sketch the diagram of the system, and then we will go from there. So first I am going to draw, I'm going to sketch a sphere which will be used to define our coordinate system. We will have our x, y, z coordinates. These are the inertial, that is fixed x, y, z coordinates, and we are going to, as we have seen, it is a good idea to in order to use the spherical coordinate frame, it's a good idea to start by drawing a latitude and a longitude to show the position of a point on the sphere. So I'm going to okay, so so here is a latitude L, and here is a longitude or a meridian M, and this is the intersection point. So this intersection point, the origin is O, and this intersection point I'll call that O prime, and there is a disk with its center at O prime, and it is attached to a bar. Okay, so the disk is attached to the end of this bar OO prime. The bar OO prime, and hence the sphere is of radius capital R, and The unit vectors that we use for solving or analyzing this problem are the spherical unit vectors. So you have ER, you have E theta. By the way, the angle that is made by OO prime with the Z axis is theta, and so you have E theta, which is tangential to the meridian, and you have E phi, which is tangential to the latitude L. Okay, and the projection of OO prime on the XY plane, we'll call that point Q, and OQ makes an angle phi. So let me just, now that we have the diagram, let me just make sure that it has the proper contrast so that you can all see. So this is the bar, and this is the disk. O prime here, Q, O here, and now there is a point P on the periphery or the circumference of the disk, and it makes an angle alpha with the E phi axis. Remember that the E phi axis, since it is along a latitude, it is always horizontal. So this is E phi, and angle alpha is being measured from there. ER is radial, and E theta is tangential to the meridian. So here is the meridian and here is the latitude. Okay, let's see. So let me also show the angle phi, the angle theta, and the radius r. Okay, so we make a note that angle theta is constant, phi dot is constant. So in other words, the bar OO prime is rotating such that O prime is tracing this latitude, okay, and it is tracing this latitude at a constant angular velocity, and that angular velocity is phi dot, right? Furthermore, alpha dot, which is capital omega, is constant, which means that the disk is spinning at a constant rate. And the question that we ask is, find the acceleration of P at a given instant, at an arbitrary instant where P is making an angle alpha. And so let me just put the title here. This is techniques of acceleration derivation. And our emphasis is still on rigid bodies, clearly, because we are considering a gyroscope, which is essentially two rigid bodies consisting of the bar OO prime and the disk rotating, and P is a point on that disk. Alright, so First we will so in this video we are going to show one technique, and that is going to be direct differentiation of velocity. So just like we had shown the direct differentiation of position as an approach to find velocities, we are going to use direct differentiation of velocity as an approach to find the accelerations. It is a pretty straightforward approach. We are going to start with this approach, and of course in forthcoming discussions we are going to invoke the ideas of using relative velocity equations to derive relative acceleration equations, and then using those relative acceleration equations directly. So that's going to be an alternate approach of solving these. A couple of things to note here. One is that we use r theta phi spherical coordinate system. It is a rotating frame, right? And we are at this point we are going to essentially take some of the results from our prior calculations, just in the interest of time, and list them here without deriving them. So the first result that we'll put is the angular velocity omega of the r theta phi spherical coordinate system. So that angular velocity is expression is omega is equal to phi dot cosine theta er minus phi dot sine theta e theta plus theta dot e phi, but since theta dot is 0, so we just have the first two terms. In this problem it has been given that the gyroscope has a constant nutation angle. We have mentioned that the angle theta is also referred to as the nutation angle, and when this angle remains constant during a gyroscopic motion, we say that that particular motion is occurring with a constant nutation, which is the case here. Another note is the fact that the r theta phi coordinate system is a right-handed coordinate system, and its unit vector products follow the following rule. So if you have er, e theta and e phi, then you have, this is a compact way of showing the cross products. So r cross theta, if you go back to this diagram, er cross e theta gives e phi, and so if you curl the fingers of your right hand from the direction of er towards the direction of e theta, then the thumb of your right hand will be pointing in the direction of phi, and so that is indicated here. Er cross e theta is equal to e phi, and similarly e theta cross e phi equals er, and that forms the loop. And if you go in this direction, you have positive solutions. If you have to go in the opposite direction, then this becomes negative. Then the answer becomes negative. So e theta cross er becomes e phi, but with a negative sign. So that is what we mean. So now the final result that we'll put together before we start calculating the acceleration is the velocity expression itself, that is the velocity of the point P, because we are looking at the direct differentiation of velocity. So we'll start off with the velocity of the point P and differentiate it. So instead of re-deriving the velocity of the point P, which is already there in one or two of the prior videos, we are just going to write the result and go from there. And we'll make a few notes as we start from here and carry out our next steps towards the accelerations. So we have Vp is equal to minus r phi dot cosine alpha sine theta er. The next term is minus r phi dot cosine alpha cosine theta plus r capital omega cosine alpha e theta, and then the third term is capital R phi dot sine theta minus r phi dot sine alpha cosine theta minus r capital omega sine alpha, and this is in the e phi direction. Okay, so that's the velocity of the point P. So just to put the discussion in perspective or in context, the expression that we wrote, this velocity expression, is the velocity of this point P, which is on the periphery of this circular disk. And now we are trying to find that the goal of this problem is to find the acceleration. So our process is going to be pretty simple. Acceleration of point P is equal to, now we'll do a term by term differentiation. Now when we do the term by term differentiation over here, we need to see which of these are variables and which are constants. So note that small r, by the way, I forgot to mention, small r is the radius of the disk. Okay, so small r is the radius of the disk, which is a constant clearly. So small r is a constant, phi dot is a constant, sine theta is a constant because theta is a constant, the angle, the nutation angle. Cosine alpha, however, is varying because alpha is varying. So this is one variable, and then er is varying. So if we differentiate, we have minus r phi dot cosine alpha. If you differentiate it, it's going to become sine alpha times alpha dot, and alpha dot is capital omega. So sine alpha sine theta, and cosine alpha differentiated is minus sine alpha. So this minus will become a plus times er, and then we will have minus r phi dot cosine alpha sine theta er dot. Right, so we will find the derivative of that unit vector shortly, but let's go through the other terms. The other terms are the following. We have so we have the next term where we will carry out the differentiation again. In this next term, we see that the only variables are cosine alpha within the parentheses and the e theta. Everything else is a constant. So when we differentiate cosine alpha, we are going to get minus of sine alpha. So I'm going to write this as plus r phi dot capital omega sine alpha cosine theta plus r capital omega squared sine alpha e theta, and then minus r phi dot cosine alpha cosine theta plus r capital Omega cosine alpha e theta dot. So this is e theta dot. Pardon my putting the dot on top of this parenthesis. It's just that did not have space. And then we go to the last term where we have to again look for terms that need to be differentiated and terms that are going to be constant. So we see, for instance, over here that r phi dot sine theta is going to remain constant, so when you differentiate it's going to be 0. So we'll have plus the derivative of this term is 0, so we have to take the derivative of this guy, which is going to be minus r phi dot capital Omega cosine alpha cosine theta and minus r capital Omega squared cosine alpha, and this will get multiplied by e phi, and then we will have r phi dot sine theta minus r phi dot small r phi dot sine alpha cosine theta minus r capital Omega sine alpha e phi dot. Okay, so one thing that you immediately notice is that when we do this direct differentiation process, we have to be mindful of the signs, etc., as we do a differentiation, and we have to be careful that we apply the rules of differentiation properly, so that we are not missing any term, and we are identifying the terms that are constant and the terms that are variable. Okay, so in this next step, what we are going to do is, let me keep this in my view. At this point it is mostly algebra, but we also need to find out this the derivatives of these unit vectors, which by now you know that the derivative of ER, that is ER dot, is actually omega cross ER, and we have the expression for omega, so that's the expression for omega. So omega cross ER, when we do omega cross ER, then you will have ER cross ER, which is 0, and then you will have E theta cross ER. Now E theta cross ER gives us negative E phi, so this is going to give me phi dot sine theta E phi. I am just going to keep the so this is my ER dot. Then we have the E theta dot, which is going to be omega cross E theta, and we do the same thing, that is, here is our angular velocity expression cross E theta. So this last term, when cross product with E theta, is going to be 0, so the only term that will show up is this cross ER, so ER cross E theta, which gives me E phi. So I'm going to have phi dot cosine theta E phi. I'm just checking to make sure that I have the right expressions. Yep. And then I have E phi dot, which is omega cross E phi, and that is going to be, so now again omega cross E phi, so ER cross E phi is going to give me, ER cross E phi is going to give me E theta, but negative E theta, so negative phi dot cosine theta E theta, because we did R cross phi, so we went in the reverse direction. And then we have E theta here cross E phi. So E theta cross E phi goes in the positive direction, so it's going to give us ER. So minus phi dot sine theta ER. Okay. Alright, so all we now need to do is substitute these unit vector derivatives in this main expression. So therefore AP is going to be equal to R phi dot capital Omega sine alpha sine theta ER minus R phi dot cosine alpha sine theta, and ER dot is going to be phi dot sine theta E phi. Right, so we have made that substitution. You can see that the terms do become quite complicated progressively, and then we have plus R phi dot capital Omega sine alpha cosine theta plus R capital Omega squared sine alpha E theta minus R phi dot cosine alpha cosine theta plus R omega cosine alpha times E phi dot, and E phi dot is phi dot cosine theta E phi. This was E theta dot. So E theta dot is phi dot cosine theta E phi. So what I am doing is I am substituting for E theta dot, and hence I have this one term. And then we have plus minus R phi dot capital Omega cosine alpha cosine theta minus R capital Omega squared cosine alpha E phi and we have plus capital R phi dot sine theta minus R phi dot sine alpha cosine theta minus R capital Omega sine alpha times, now E phi dot is minus phi dot cosine theta E theta minus phi dot sine theta ER. Okay, so let's see if there are any cancellations that potentially will happen at this point. I don't see anything. I take it back. I think this R capital Omega phi dot cosine alpha cosine theta E phi will cancel. Oh, rather this is negative and this is negative as well, so it will get combined to form one term. Okay, and these will give rise to E theta and ER terms. Okay, so what we can do at this point is we can start collecting terms in the individual along the individual unit vectors. So let us first collect the terms that have ER that have ER in them. So we have R phi dot capital Omega sine alpha sine theta. This has a ER, these don't, and then we have these three terms multiplied by minus phi dot sine theta. So we have r phi dot squared sine squared theta minus small r phi dot squared sine alpha cosine theta sine theta. And let's check the signs, because this is going to be minus, but this one is going to be a plus, and so is the next one, r phi dot capital omega sine alpha sine theta. This whole thing will get multiplied by er. So one thing that you can see here that this term and this term are going to get combined. So these are all the terms that have er in them. Next, let's put together the terms that have e theta in them. So r phi dot capital omega sine alpha cosine theta plus r capital omega squared sine alpha, that has e theta. And then we'll have e theta coming from these three terms multiplied by negative phi dot cosine theta. So we are going to have minus r phi dot squared sine theta cosine theta. We are next going to have plus r phi small r phi dot squared sine alpha cosine squared theta. And then we are going to have r capital omega phi dot sine alpha cosine theta. Now let's see if there is any combination or any cancellation that's happening here. Indeed, these two terms get combined. So there are two terms getting combined just like in the ER expression. Yeah, and lastly we put together the terms that have e phi in them. So if you go back, here is one term, here are two more terms, and here are two more terms. Okay, so there are 5 terms that will have e phi in them. So we'll have minus r phi dot squared sine squared theta cosine alpha. That's a negative term. And then minus r phi dot squared cosine alpha cosine squared theta. Phi dot squared cosine alpha cosine squared theta. Yep. Then we have a minus r capital omega phi dot cosine alpha cosine theta. And then we have these two terms. So we have minus r phi dot capital omega cosine alpha cosine theta, the negative sign. And then we have minus r capital omega squared cosine alpha. And this is all in e phi. Now here again I see a couple of terms getting repeated. For example, this one you have a sine squared and cosine squared, so they will add up. These two are repeated, so they will get added up, and there will be 2 times each of this term. Okay, so we have a little bit of a simplification here. So the final expression for the acceleration of the point P, which as you can see is quite complicated, and this is typical of acceleration expressions because it is another level of complication from velocities. So there are added terms that show up. So let's see, we have 2r phi dot capital omega sine alpha sine theta minus r phi dot squared sine squared theta. plus small r phi dot squared sine alpha cosine theta sine theta, and this is ER, plus now we add all of these together, and we did notice that two terms are going to get added. These two terms are going to get added, so you'd have 2r phi dot omega sine alpha cosine theta plus r capital Omega squared sine alpha minus r phi dot squared sine theta cosine theta plus r phi dot squared sine alpha cosine squared theta, and this is the coefficient of E theta. And in the ER direction we also have a couple of additions, so we have minus r small r phi dot squared cosine alpha, because here we have a sine squared theta and a cosine squared theta that get added up, minus 2 small r capital Omega phi dot cosine alpha cosine theta minus r capital Omega squared cosine alpha, and this is in the E phi direction. So that then gives us our acceleration, and it is a rather complicated expression, but that is kind of expected, as we mentioned that accelerations are since they are fundamentally derivatives of velocities, so they are more complicated than velocity expression, because terms in velocities get differentiated to give you the acceleration. One thing that I would mention here, and we have touched upon this previously, whenever you use the direct differentiation approach to find a vector, say velocity or acceleration, it is very important to remember that if the question is to find or if what we are trying to find is the velocity at a certain orientation or acceleration at a certain orientation, and that's a specific constant given orientation, then if you are trying to find the velocity at that orientation, don't enter the orientation values in the position and then do the differentiation. That is not going to give you the right answers, because let's say, for instance, we were trying to find the velocity when alpha is equal to 0. So if you put alpha equals 0 in the position of p and differentiated, you wouldn't have gotten the right velocity, and that is because you are imposing a constant position before differentiating. So always the idea will be to first differentiate and then impose the condition. Okay, and the same thing happens for acceleration also. Let's say I'm interested to find the acceleration when alpha is equal to 0. I should not take this velocity expression. This was our velocity expression that we started from. Let's say I was interested to find the acceleration when alpha is equal to 0. I cannot take the approach of substituting alpha equals 0 here in this expression and then differentiating, because then I'm no longer treating alpha as a quantity that changes or alpha and contributes to the acceleration. I'm stopping that from happening when I take the differentiation, and so the answer that I get is an incorrect answer. Okay, so what we should do is take the general form of the velocity, differentiate it with respect to time, and get the acceleration, and then impose the condition. So if you have to impose or find the acceleration at alpha equals 0, don't impose alpha equals 0 here and then take the derivative. Rather, do the derivative as we have done here, go up to this point, and then impose alpha equals 0. So here, for example, you would impose alpha equals 0 at various places where alpha shows up, and that's going to give you the right expression for the acceleration if you are interested in finding the acceleration of the point P when alpha is equal to 0, or for that matter any other angle. So when doing direct differentiation, remember that first do the general differentiation and then substitute the specific condition. Don't substitute the specific condition first and then carry out the derivative, because that way you are not capturing the variation of the different variables. Okay, here alpha is a variable that is changing, and if I put alpha equals 0 here and then take the derivative of the velocity, I'm not capturing the acceleration that is contributed by the fact that alpha is changing, right? So I need to incorporate that first and then impose alpha equals 0. So that is something to keep in mind whenever you use the direct differentiation method, either for finding velocity or for finding acceleration. All right. Other than that, the direct differentiation method is quite straightforward. It can be tedious because, as we saw over here, we have to be very careful about taking the derivative of all different terms that are varying with respect to time, and we have to be careful about taking the derivatives of the unit vectors. So often this direct derivative approach may become a bit tedious, and some of this lengthy calculations can be avoided if we take the direct acceleration expressions that arise from the relative velocity expressions, the three-term relative velocity expressions. And so that approach will be discussed also for this particular problem and for other problems. So that's it for this video. Thank you.